Previously we've looked at a bit of statistics, and here we had some data. A was 9 and 3 and 6 across 3 cases, and B was -2, 0, and -1 again across 3 cases. And here I happen to label it R. You can call it X and Y or whatever, maybe percentages, or maybe pigs and dollars. And if you look at the data, which is always a good idea, the A are the red dots and B are the blue dots, and they seem to be kind of negatively correlated. And we're going to, of course, calculate the mean. And for A, that's the 9 and the 3 and the 6 added up, divided by 3. That's 18 over 3, 6. And B is the -2 and the 0 and the -1. That's -3 over 3 is -1. And here, let's make a table of differences. The differences being +3, -3, and 0 for A, and -1 and 1 and 0 for B. And as a check, these should always add to 0 at this stage because the mean is halfway above and below the data. And what we're going to do next is calculate the variance, the variation of those differences from the mean. And we're going to take each of those differences, there's a little table again, and we're going to square them. And the 3 squared is 9, -3, minus times a minus is positive, is another 9, 0 is a 0, and so you get, 9, 18 over 3 is 6. In the case of B, the -1 is squared, making it positive. Another 1 squared, another 1, 0, 2. 2 over 3 is 2/3. Now what we do next is take the square root. As a mnemonic device, I didn't do that pig-dollar analogy by accident, because it kind of helps remind us that notice the variance for A would be pigs squared. The only place I know that exists is maybe in a can of Spam. And in the case of B, that would be dollars squared, and that makes no sense. So let's take the square root. And what do we get? Square root of 6 and the square root of 2/3. And at this point, we can go a couple of directions. The classic one is to continue on and compute the covariance, the covariation. And, we go to our table of differences, and we're going to look at A, starting with case 1, the +3 times B's case 1 of -1. And then the second case for A is -3, and the second case for B is +1. And then we have 0 times 0. So we have a -3 plus another -3 plus 0, -6 over 3 gives us -2. That's the covariance. And Pearson thought of what we're going to do next, and that is recall that these are in pig-dollar units for the covariance. That makes no sense. But the standard deviations are respectively, say, pigs and dollars. And what if you divided the standard deviations into the covariance? We call that the correlation. And so that would be the -2 divided by square root of 6, and again divided by the square root of 2/3, and that's a square root of 4, which is 2, and the -2 gives us a -1. The correlation is -1. And you know what? Looking back at that graph, that's what we would think. As an aside, going in another direction, and maybe to show how this stuff is really useful, one could, and I'm not going to show it, one can compute what's called the beta, the slope, how you predict one from the other. And that happens to be the covariance divided by the variance of the one you're choosing to predict from. Well, the variance in case of A is 6, or the variance in the case of B is 2/3. And if you divide that into the covariance as -2, in the case of A, you get -1/3. In the case of B going to A, you get -3. And sure enough, look at the table. Going from A to B, you would multiply times -1/3. But going from B to A, you would multiply times -3. I like to think of the beta, that slope, that covariance over the variance, as your directional aim of your arrow or cannon, whereas the correlation, which notice has no units, is the accuracy of your aim. In a continuation, we might know that whenever you're dealing with sample statistics, you can be wrong in two different ways. Sometimes it's called a type 1 error and a type 2 error. Type 1 error is where you fail to recognize something when it's there. Type 2 error is you recognize something when it wasn't there. And you might be looking at two different groups. One had the placebo. You've heard about the new improved placebo, I presume. And you're maybe titrating the little rats to either survive or die, whether or not people like the new cheese-flavored treat, and so on. So to illustrate this, I did a number of simulations with evenly distributed numbers between 0 and 1 and computed the moving average and calculated something that we'll look at, confidence bounds. And you'll see there's an upward one and a lower one here. And generally, as we go across the simulation, it may bump against the confidence bound on the top or the bottom. But do notice it does become narrower, as we will see by the inverse of the square root of the sample size. And wait a minute, look at this one. It went outside the boundary. And indeed, that can happen. And here are the equations for the confidence bound as well as the requisite sample size. It's the standard deviation divided by the square root of the sample size. Here I'm going to make the standard deviation 1. That's normalized if you like. That's minus the mean divided by the standard deviation. And in the case for the confidence bound, well, let's see. We have, let's say, 100 cases. Square root of that's 10. Divided in, we get 0.1. Let's go to, say, 400. Square root of that's 20. Well, 0.05. And so on. All the way down to you need 10,000 cases. Square root of that is 100, which means you get a confidence bound of 0.01. And from either one, you can calculate the other. In the case of the sample size, you take the square of the confidence bound and divide it into standard deviation. So wrapping this all up, I probably should give you some academic shortcuts, wherein if you look at any old paper, you probably just go right to the conclusion, look at the tables, and by convention, they tend to highlight the 0.01 significance levels with 3 asterisks, 0.02 with 2 asterisks, and 0.05 with maybe 1 asterisk. And sometimes you look at 0.1 levels because you don't have a large enough sample, or it doesn't matter. You want to hold a more severe significance level if you're doing something really severe or employment. With Dr. C Invests.